Just a couple of things to say at the start. Um, so again, most code is given to you. It's really only things that are specific to looking at goodness of fit and comparing models that is not given. In this case, we are using some of the object-oriented capabilities of Python, including inheritance. If you haven't done this before, the structure is there already, so hopefully it isn't a problem. And if you haven't seen it, then now you will have seen it. Otherwise, go for it. You're going to be looking at posterior predictive plots and calculating the DIC and the evidence. And, ask questions whenever you need to. Okay, are we ready to go over things? No one's going to feel put out if we go over the notebook, at least my solution to it. Okay. All right, so this was our data. And I just want to point out, this again was not a line fit like the problem I gave you yesterday. And it was not a Gaussian problem like the problem I gave you yesterday. And in fact, I'm pretty sure this is the PGM for it, including the model assumptions. It's pretty much the simplest inference problem that I can think of where we are fitting for the distribution that the data come from, period, and that's it. That's all there is to it. And I'm just mentioning that because that simplicity often throws people off. They're expecting to see something with a chi-squared or something along those lines, or with an x and a y, right? Okay, so there's a bunch of things, and many of the bits of code that you were asked to put in were relatively simple. So that's just to say, if there's something that you want to see the code for, like wave as I go past it, because otherwise I might skip. So a test statistic, let's just see the one that I used. You can see that I tried a couple of things, but it was the number of data points that were less than 100 kiloparsecs in the offset. So basically, what fraction of our distribution is down here pretty close to zero distance? That was it. Not what we actually did in the paper, but it's something that you can do. Okay, so we had the code for the exponential model up for a while. Is there anything in particular in this that people would like explained? I think it was largely an exercise in just understanding what are each of the things that we need to do, and then in some cases knowing that scipy.stats can do it for you. Okay, so we move on. I believe that there's nothing actually to fill in for a while, but for example, here is a mock data set according to whatever choice of parameters went in there, just showing that it all works. Fitting the model, this model usually does not cause much of a problem. You just need to have a guess, which is the right order of magnitude, so not 1,000, but maybe 100, and enough steps that you actually can see something. Did that work for everybody eventually? All right, MC is pretty decent with one parameter. So just going through, we calculate the mean value of A1 just for later, happens to be close to 100. There's all of these plots that are more or less completely given to you after you have a fit. So the posterior mean, it doesn't quite reproduce what the data is doing, but it's not completely crazy. There's comparison of one mock data set with the truth. Doesn't look that great, in fact. There's this really fancy thing comparing many mock data sets with the true data, which looks a little bit better, but you can still see here at the center, we're not really reaching the high values that we have in the real data. And here, we're over-predicting a bit. It's kind of hard to say exactly what's going on here. So some hints that maybe this doesn't work really that well. So getting quantitative, what were the things that you actually had to do here? So calculating the p-value, this could be done pretty simply once you have the code to generate mock data sets and calculate the test statistic. You just do that. I guess that was given earlier. And then the p-value, once you have a list of test statistics for replica data sets, it's really just the fraction of those replica t's that's greater than the t you calculated on the real data. Nothing more complex than that. So here we go. Somewhere it will say what it actually was. Oh, okay. It was 0 for this particular choice of statistic. So you can see, really? That doesn't seem right. Maybe it's rounding, yeah. There were a couple, presumably, that were higher than this value, but not a lot. It doesn't look great, right? Okay. So how many people got as far as calculating the DIC? Just show of hands. A few, okay. So, let's see. Given our posterior samples of the model, this should be relatively straightforward. We actually had a cell block in the lecture that more or less did it. So you can just do the averages over the posterior that we talked about. I'll show the code if people want to, but otherwise we'll just go past. Interestingly, the number of free parameters is magically pretty much 1. I don't know why this works, but it does. And you have the DIC value here. This on its own is meaningless. If we had twice as much time and you went through all of these steps with a different model, you could compare the two of them. Okay, computing the evidence. Did anybody get as far as trying to compute the evidence? Fewer, but some. Okay, so it might be worth just a couple of comments about this. So this is sketching out a simple way of doing the integral, which is just a terrible, terrible idea in large parameter spaces, like exponentially bad in large parameter spaces. But one thing that you can do to estimate this integral in principle, and it's completely unbiased and mathematically beautiful, is just generate samples from the prior and take an average of the likelihood over those samples. You can kind of visualize how in many dimensions this doesn't work very well because the volume of the prior space becomes huge and most of those likelihoods are very close to 0. But in one dimension, it's okay. So again, all of the solutions are already on the GitHub repo with just 2 errors, or one to 2 errors that people here found that need to be fixed. And that will happen later. So we can do this calculation, and I suggested looking at what happens with a few different total numbers of samples that go into the average, just so that you can convince yourself that you're seeing something eventually which is stable. So I changed this line to include not just 1, 10, and 100, but also 1,000, 10,000, and 100,000 samples from the prior. And you can see that there's some change from one to the next, but by the time we get to many, many samples from the prior, we're basically getting the same number at the end. And if you remember that Jeffrey's scale for comparing evidences or information criteria, differences, in the second decimal place here are not really significant on that scale. So we should be okay here. So of course that's not really the end. What you would do in practice is you would have an alternative model that you think might do a better job and basically go through these steps again and calculate a DIC and an evidence for those things and compare them. But we clearly don't have time for that today. So that's the challenge problem if you want to do that on your own. And of course, yes, you've already this week, you've actually used Dynasty. And so it would be interesting to see if that gives you the same answer as the silly Monte Carlo integration, which it should.